is here, and we are very thankful to have him today. He's a professor here in mathematical physics. He's also an associate faculty at the Institute for Quantum Computing, an affiliate faculty at the Perimeter Institute. He is part of the Relativistic Quantum Information group here in his research, and he teaches a variety of undergraduate and graduate level courses. So please help me in welcoming him.
Thank you. All right, thank you very much for coming, and thank you very much for the invitation. That was nice. Yeah. Pure Math Club, is that okay if I call it Pure Math? Okay, fair enough. So Pure Math Club, thank you very much, guys, for the invitation. So I see some known faces and some more not so known faces. So there are known ones, those of you who have taken general relativity, some of the things that I'm going to tell you, you have been exposed already to them. So I would ask you, I'm going to ask for opinions here. You guys are not allowed to participate if you know too much, all right? Well, if you know too much because of me, okay? All right, anyway, so I want to say a little bit about relativistic quantum information. So this is a little bit of an intro of what this field is about, all right? Let me say that there are 3 groups of relativistic quantum information in Waterloo, which makes it, I think, the superpower of relativistic quantum information in the world. The 3 groups are Achim Kemp's group in applied math as well, mathematical physics like me. Rob Mann in physics, but Rob Mann does many, many things, among others relativistic quantum information, and myself and my group as well. Okay, actually, at least I see one of my grad students is here, I can see, so you're not allowed either to participate in the questions. All right, so again, thanks a lot, guys. So let's begin, and let me just walk you through a little bit about, I don't know how many of you know relativity. In particular, many times you'll hear things like relativity, space and time are the same kind of thing. Yeah, yes and no, in the sense that if you think of space-time as a 4-dimensional manifold, something like that, and then you have, at a given point, you have coordinates and you think, oh, I have my space, I have some rulers that allow me to measure, and I have my watch that allows me to measure time. Well, there's something peculiar about time, right? In particular, I can move in any of the 3 directions arbitrarily, whereas moving through time is a little bit more complicated. I can definitely move through time in different trajectories, but it's quite tough to go backwards in time. All right? And that makes time a little bit special. Time is not really on equal footing, if you want, with the other dimensions for a given frame. So let's just get a little bit familiar. So you see that someone said once, well, of the 4 dimensions of space-time, if I had to choose one along which I'm going to be dragged all my life towards one direction, let it be time, right? Anyway, so space-time. So here's the usual way we represent space-time. And we have this dimension here representing space, and the vertical axis represents time. Okay, or proportional to time with some proportionality constant. So the proportionality constant is the speed of light. So that allows us to separate like 45 degrees lines coming from the origin if you want. So from lines that are have an angle larger than 45 with the x-axis and smaller than 45 degrees with the x-axis. So a couple of examples of motion through space-time. Moving through space-time when you're at rest. Like for example, you right now, more or less. So you're still moving in space-time and your trajectories are like that. You're moving towards the future, all right, towards your future. Our common future, I would dare say, because more or less we all have the same reference frame here. Okay, this is another example. We are communicating, we're looking at each other, we send light to each other, light bounces off and gets to ourselves. So you see that's what happens when we send light. So at some point I send a signal, and the signal reaches someone else at the back of the room at some time in the future, in particular, the light crossing time of the room. All right? So far, so good. Things that we can do, indeed, is start walking like this. So my position would vary. So that's fine, that's allowed. We can move slower than light. That would be motion if I start running pretty fast, to be honest, if I go like that. But I start running pretty fast, right? And that's the way I would go. Let's just forget about the catastrophes that couldn't actually ensue after me going that fast in an environment with an atmosphere and stuff like that. Let's forget about that. But then again, we can do that. That's fine. What we cannot do, at least in special relativity, is something like that. If I have time, we'll discuss a little bit that in general relativity, well, not that much maybe, but it's not so forbidden as such. Or in a way, okay, so we'll talk about it, maybe. So the way I designed this talk, it's designed not to reach the end. It's designed to be thorough until we reach a point in which time is over, okay? Because that actually transmits very well the idea that relativistic quantum information is a vast discipline, all right? Anyway, so maybe most of you, because this is a math faculty, right? And also there are physics people here. You will have seen Lorentz transformations, and you know that time and space, if we measure distances and times, they are relative. They depend on the observer. So if we say 5 meters, we need to specify 5 meters according to whom? Who's measuring those 5 meters, all right? In particular, the axis of one observer and the axis of another observer are related through Lorentz transformations. And in particular, a transformation, so we're looking at 3 events here. So imagine this is us at rest, and then at the same position that we are, we have a rocket passing by in one direction and a rocket passing by in the opposite direction. And we're going to describe events A, B, and C from the perspective of the 3 observers we have here. So if we are the ones at relative rest, if you want, just let's declare ourselves being at rest, and say that we see 2 simultaneous events. What does it mean to be simultaneous? Well, it means happening at the same time at 2 different positions. Let's define that as simultaneity. Makes sense kind of thing, no? It's kind of the intuitive concept of it. So we look at this and we would say, oh yeah, A and C happen simultaneously, okay? However, someone traveling a rocket at our same position would disagree with that. In particular, someone traveling at 1/3 the speed of light would have different axes, and someone traveling at minus 0.5 times the speed of light in the opposite direction would see the events happening like that. Those are the planes of simultaneity for the 3 different observers. And in particular, simultaneity is a relative concept. So it's not true that A and C are simultaneous in general. It's true for me, but other observers would disagree. For example, in this case, that's actually wrong. C happens after A, right? It goes like this. So C is hit first and then A happens. And in the other one is the opposite. Yeah, it says the same in both. So obvious typo. A happens. No, it doesn't. Damn it. Not so obvious typo. A happens after C, before C, right? So different observers would disagree on what is simultaneous. The concept of simultaneity of what happens first, if we talk about space-like separated events, events that happen separated by space, what happens first depends on the observer. Typical example is the twin paradox, okay? So in particular, you take 2 twins, and one of them stays on Earth, the other one travels to Alpha Centauri in a rocket, and we say, okay, fine, so I'm going at 0.8 the speed of light, I have a very good rocket, and it's about 4 light years, so that means that the mission time would be 10 years per leg, right? 10 years to go, 10 years to come back. Then you do the math, right? And then, yeah, sure, the mission, no, sorry, twice, it's already twice. So 5 years per leg, and then that makes it 10 years, one back and forth, right? And then if you do the calculations from the spaceship reference frame, what you get using the Lorentz transformations that I showed you before is that actually when the other twin comes back and talks to his brother, he actually would say, he arrives and said, look, well, the guy actually on the ship would be like, right, so I'm supposed to take 5 years to get there, but I only took 3 to get there. What's going on? And what he thinks is like, well, we measured distance wrong. I can't believe it. We have very good methods to determine distances from nearby objects. We use something called parallax. It's actually pretty good with the observational evidence we have. How come we actually measure it wrong? There's something bad here, something's going on, I'm going to go back to Earth. And the guy goes back to Earth and says, look, brother, I've been away only for 6 years. We measured the distance wrong. Actually, the distance to Alpha Centauri is only 2.4 light years instead of 4. And the brother says, well, what do you mean? I mean, you've been away for 10 years. You've done the whole trip. So, of course, how long it took would depend on who you ask. All right? And, of course, one of the brothers is actually older than the first one. It's actually pretty easy to see graphically. So imagine this distance, and this distance corresponds to 1 year. 1 year as measured by twin number 1, 1 year as measured by twin number 2. And here, the planes of simultaneity for twin number 1 is just constant x, right? So this guy here counts 1, 2, 3, 4, 5, 6, 7, 8 years, let's say, in a period of time. But the other guy travels in this direction, then accelerates here to come back, and then goes back. And the planes of simultaneity are this, 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 this. So this guy counts, all right, so 1, 2, 3, 4, 5, 6. I missed 2 of them, all right, because of me going pretty fast. Like if I don't go fast enough, these guys are not going to be tilted as much, and you're going to measure the same amount of time. But if you go too fast, you're going to measure different times. So time is relative, okay? Simultaneity is relative. And actually, the way in which many people many times illustrate this is through something called paradoxes that you guys might be familiar with. Paradoxes in relativity are ways of posing a problem in an ill-defined way, actually making mistakes in the way we pose a problem to make it look that it's contradictory, but what happens is we actually don't know how to solve it if we do it like that, okay? So let me show you 2 of them, and I'll ask for opinions, right? And this is the last thing I promise for those of you who have seen this before. Let's do the Bell rocket paradox. As I said before many times, we are here, which is the universe where theoretical physicists live in. And here, typical universes where you have spherical cows of mass 0 and stuff like that. And as I always say, these are rockets in that world, okay? And those are 2 rockets that are tied by a rope. And the rope is a pretty flimsy one. This rope will actually break the moment there's any kind of tension in it, okay? So what these rockets do, they just lift off like that, okay? And then we ask the following question. Does the rope break or does it not? So the 2 rockets accelerate. They have identical fuel, identical engines. Not only that, they live here, where identical means identical. There's no room for engineering here, okay? Identical means identical, exactly the same. So they both measure, in their instruments on board, measure the same proper acceleration, the same acceleration. They have just an iPhone, for example, with the accelerometer on, and they measure exactly the same acceleration, okay? So, well, yeah, there's the why thing. Again, why might not be, so it's very important to say that actually physics answers hows and no whys, okay? But we can always look for whys every time. Why is a question that can have answers that don't satisfy everyone, and rightfully so. You can keep asking why all the way through, okay? There's no limit to why. Physics replies to hows, and then humans in the minds make up answers to becauses, right? Answers to whys, to feel better with ourselves, all right? So that's what we're going to try to do now. Okay, so space-time, the 2 rockets following an accelerated trajectory. If it's constant acceleration, describe hyperbolic trajectories here. You can, if you don't trust me, which is healthy, what you should do is go back to the Lorentz transformation and integrate in a trajectory. You get nice cosine, hyperbolic sines, as some of my GR students already know, right? Okay, so seen from Earth. So I'm at the control tower there, and I look at these 2 rockets going by, and I see at the time t1, the 2 rockets are there. They go with the same acceleration. At the time t2, the 2 rockets are there. Okay, so the distance between the rocket is constant. Therefore, I conclude the rope would not break because they're going like this at the same speed, right? So therefore, the distance is constant between them. Now, someone else, in particular, the operator of rocket 1, let's say, doesn't see things the same way. This guy is gaining speed, or lady is gaining speed. And it's gaining speed so that at time 0, the plane of simultaneity, it's here. So it coincides with me at the control tower. But at some time, this guy is going to acquire some speed, right? So therefore, the planes of simultaneity will not coincide. In particular, if we drew them, right, that's plane of simultaneity number 1, that's T1 for the guy, that's T2 for the guy, which is kind of interesting. You mind if I kick this to close the door? Yeah, getting distracted by people, sorry. So, right, so look at that. The distance at T1 and the distance at T2 is different. And in fact, is larger. And in fact, this guy looks at the other rocket and phones the other rocket and says, hey, you were supposed to go with the same acceleration as I'm going. What are you doing? You're going too fast. And this guy said, what do you mean we're going too fast? And I go, yeah, you should set it for 9.8 meters per second squared, for example, of acceleration. That's what our instruments say, and you're going at 12. And this guy said, what do you mean? No, we are going at 9.8 meters per second squared. You've fallen behind, you're going at 7. So that's what they would see from the respective frames. Interesting enough, from the point of view of this guy, the rope will definitely break. Because, the other ship is going away. So indeed, it's like you have two rockets and one is like, woo! So the rope breaks, okay? Now the question for those of you who don't know this paradox from before is, the thing is, does the rope break or not? And then once I showed that to someone and they told me, oh, it depends on the observer. No, it doesn't. Like, if someone afterwards says, I want to borrow your rope to do another experiment, can I use it? I don't know. For me, it's broken, but maybe you are someone else. No, it doesn't work like that. That's physics, you see? The why is phenomenology, is coming up with an explanation why it does or it doesn't in the no-intuitive reference frame. That's our why. Okay? But physics is, does it break or not? The rest is what we call phenomenology. How does it manifest in a particular frame? So I want to take like a little poll here. Does it break or it doesn't? How many people think that it breaks? Hands up. No abstentions allowed. You have to go one way or another. So we have about 1, 2, 3, 4, 5, 6. You're not allowed to participate.
You said no abstentions.
Cool. 7 people breaks. How many people no breaks? Okay, it doesn't break. Like the majority, you always go. Oh, the majority always goes with it won't break. The answer is actually that it breaks. And now, and this is how you want. Now we want to feel better with ourselves and give a why to it, right? A because, I guess, answering. So let's depart from physics and go to phenomenology. From the point of view of the accelerated observer, it's clear that it breaks, and the answer, the because, is, well, because rocket B is faster than us. So, well, they're leaving us behind. So it's breaking. What would be the answer for the other frame? For the other frame, so you remember, guys, what happens, maybe you haven't seen it, but you know what happens with extended objects that gain speed? So what happens if you have something of length L, and I start accelerating and it goes to speed V? Do I see it with the same length? Or is the length contracted according to me? It is, huh? So from the point of view of the observer on the ground sees 2 rockets at the same distance with each other at every time, but there's also an extended object, which is the rope, that is moving at speed v, increasing speed, so this guy experiences a Lorentz contraction. So the way that someone in the ground would see it is that thing is kind of trying to contract, but it can, and it breaks. Okay? So there's extra tensions coming from the differential acceleration that they feel in here, and there's extra tension coming from the fact that there's no solid rigid in special relativity. So yeah, it breaks, huh? Who would have told? There's others. Yeah, you see, the interesting thing is that, again, the physics is the same, but the descriptions from different frames are different. So other paradoxes, for example, is this one, is the bar and the grating kind of thing, the bar and the hole, if you want. So we have a bar here, okay, of length L. And we have 2 people. One is riding the bar. The other one is watching it from outside. Okay? And then the one in the bar, like riding the bar, would say, right, my bar has length L. The hole has length L prime, smaller than L. I don't fit in it. So I would just go over. Not only that, I'm going at relativistic speeds, so Lorentz transformations tell me that the length of the hole would be contracted because the guy at the bar, of course, sees the bar at rest. It sees the wall moving. So this hole is moving, and the length will contract. And therefore, not only I don't fit because I'm longer when we are at the same reference frame, when we don't have any relative speed, I would not fit even because the Lorentz transformation would make this guy even smaller, so I would definitely not fit, and I can continue. However, from the perspective of someone standing here, is saying, okay, yeah, I know that length, that bar was actually longer when it started accelerating, but now, because of Lorentz transformations, because of the fact that it's gaining some speed, I'm going to see the bar getting shorter, a Lorentz contraction. Therefore, it's going so fast that it's going to be shorter than the hole, and the bar would fit in the hole. So it should fall in the hole. And again, same as before, there's some physics. Physics is, where do I have to look for the material that made up the bar at the end of the experiment? Should I look down here, or should I look somewhere there? What do you guys think? How many people would say it doesn't fit? Does not. Hands up, hands up. How many people would say it does fit? Good. In this case, I think the majority got it right. It definitely fits. And what happens, to fall to the grade, you actually need something that I didn't mention before. You need a little bit of gravity, right? Otherwise, you would not fall. You just go and slide through. But the problem is that, okay, for this observer, for sure, it fits. So that this observer sees the bar getting smaller, and then he sees gravity acting on it and falling, and he actually sees the bar curving. And from the point of view of the bar, what happens is that the moment this bar is exposed to gravity, the moment there's no floor anymore that has a reaction force compensating for gravity, the gravitational pull that this guy is going to feel is not 9.8 meters per second square. You need to transform acceleration too. And in particular, also as my GR students know, there's going to be a transformation of acceleration in the perpendicular direction to motion as well, right? Yeah, and it's actually huge. The transformation, if you go at high speed, is so huge that that acceleration is so tough that there's no material that can resist it. Actually, you can prove it. The only way to resist it is being able to have a material that can signal faster than light. So it's impossible for a bar to actually not fall. The bar would definitely be forced. It's like a horizon. In particular, actually, it's literally a horizon. The bar would see a horizon that cannot go through, and that horizon, it's below the length of the grade. So the bar would just go down, and it will bend. Not only bend, it will probably break. And if we go realistic here, what would happen is that the whole scenario would have gone in a nuclear explosion. But in any case, if it were super ideal, right, and things only bend and stuff like that, and there's no atmosphere and no friction, which is the main point, if you get things to accelerate too much, the nuclei get too close to each other, and they don't like that, and they actually like it a lot, I'd say, because they tend to react and release vast amounts of energy, and we call that H-bomb usually. Anyway, so these things, right, these problems illustrate that one cannot rely on Galilean intuition, which is our intuition because we've been exposed to it since we were kids, to talk about relativity. All right, any questions so far? Good. Yeah. Okay, so remember, relativistic quantum information is called relativistic quantum information. So the quantum bits. So I'm guessing here that some of you have been exposed to some quantum, some others may have not, right? How many people here have been exposed to quantum academically? All right, quite a few. How many have not? Okay, but those of you who have not probably know about Schrödinger cat, no? Ever heard about it? So Schrödinger cat, it's basically a superposition of two. So in quantum mechanics, if you want, observable states of physical systems, states that you can observe, are eigenstates of self-adjoint operators. And the nice thing about it is that any states that are allowed are actually live in the Hilbert space, expand by the eigenstates of those self-adjoint operators. So interesting enough, you can have a cat that is alive. That thing represents a cat that is alive. That thing represents a cat that is dead. So in particular, a linear combination of the two states is also a valid state. So you can have cats that are dead and alive at the same time in a way, or I would say not dead, not alive. It's a different state. They don't have a definite value of the variable life. Okay? That's the way you would say it. The expectation value is actually half between the two, and the uncertainty is of the order of the whole range. Okay? So you don't know if you have a dead cat or an alive cat. Question for you. So can I imagine that I start throwing you cats? Okay? Like I have a bag of cats here, and then I just throw cats to you, and you check them. Some of them are alive, some of them are dead when you check them. Could you, and I promise to you, okay, cat, and now I'm throwing you Schrödinger cats. Can you tell if I'm not? So there are two possible scenarios here. I have a bag with half of the cats being dead, half of the cats being alive, and then I just throw them to you. and then I tell you, no, it was you, when you observed it, that killed it, or whatever, right? And then the other option is I have here superpositions of alive and dead cats at the same time, and then throw them to you, and when you measure them, you find half the time you find it's alive, half the time you find they're dead, okay? Can you distinguish between the two? Well, just checking if they're alive or not, you cannot. But there are other experiments that can distinguish between the two. For example, you can get the cats and throw them through a double slit, okay? So if you do that with the cats, in particular, because of the fact that alive cats and dead cats don't make the same imprint in a double slit experiment, alive cats will try to resist. And therefore, they're slightly different. What you would see on the other side of the grate, the splatter or whatever, is a little bit different. Yeah, I'm so sorry. I really love cats. It's really cruel. It's not me who decided to use cats for that. It was this guy. Anyway, so let's not call it splatter. Let's call it pattern. The pattern, the interference pattern, what will look like if you look at the other side of the grid, right, is different if you throw alive cats or dead cats. And in particular, if you throw dead cats, live cats, and this, they have different patterns. You're going to see blurrier or no blurrier splatter, right, depending on what kind of cats you had there. So you can distinguish. There are cases where you can definitely tell. And, we need to get used to that. Things can be dead and alive at the same time. Things can be in two places at the same time. Okay? You know what? It's actually something learned. We need to learn that things are not in two places at the same time. Like everything, when we're babies, we're exposed to the world, and everything seems you know how easy it is to fool a 1-year-old? You can make them believe almost anything you want if they feel safe with you. It's kind of, anyway. But what I mean is true, like they trust people because they have no other ways of learning. So if people tell them things, they would believe it. In particular, they make assumptions, like there's these experiments on YouTube that you can see where they hide a little ball like this, and they put like a little glass on top that is opaque, and they ask the kid, where's the ball? In there. And then what they do is they put it in, and when the kid is not looking, it's, oh, look at that, they remove it, and say, where's the ball? In there. They remove it. Oh, it disappeared. You know how easy it is to do like magic tricks with kids, right? Not because kids are stupid, they're actually super intelligent. You know how fast they can learn foreign languages? Like this, without realizing. Their brains are the most powerful of all the brains of human beings. They have the highest slope of the learning curve. So do not underestimate babies. In the same way, do not overestimate professors, because you guys are more plastic than professors because of just age. The difference is that we're higher in the learning curve. We've been learning for a longer time. Not because we get it earlier, it's because we've been doing it for longer, okay? Same with babies. Your advantage is that you've been doing this for longer, and they haven't. They have to learn that actually things can disappear without looking at them. And in particular, they have to learn that a ball, that you get some object, and the object cannot be in two places at the same time. So, no, that's ridiculous. Why? Because I've been living my life all these years, and I've never seen the opposite. That's the only reason they can tell you. So if you're a mathematician, you know that is, of course, ridiculous. You can actually change your paradigm, no problem, and you can work consistently from there. And if you're a physicist, you know that people do experiments where actually things are in two places at the same time. So we need to give up prejudices that we learned since we were kids and open our minds, and that's why math is so useful, because math allows us to write things in a subjective way. Math is the language in which we write physics, okay? Because remove subjectivity, okay? No, but I don't care. Do the calculation, but no, just do the calculation. Not true, you need to understand what you're doing, but what I mean, if someone has some opinion about how the world works and it contradicts, starting from the same hypothesis, contradicts what the math say, chances are that person's wrong. Chances meaning 100%, anyway. So there are cats. Quantum superpositions, already understood. Something funny. So when this is a real New York Times. Actually, it wasn't like that big, but it was on the first page anyways. It was a small mention on the small, but kind of decent mention on the first page. So yeah, physicists in the past, they met together and they made the headlines of newspapers. And in particular, this is talking about the Solvay conferences and all the papers that came after that. And in particular, it was trying to reconcile relativity with quantum theory because of something funny that people found. The great debates, if you want to read them, is Einstein versus Bohr, Niels Bohr. Two people that are not known for being stupid. So they argue really, really well, both of them. And in particular, this is referring to something called the EPR paper, okay? Einstein, Podolsky, Rosen, okay? So Rosen also is famous for wormholes, like same as Einstein. The first wormhole-like solutions to Einstein equations that were found. Podolsky was a great physicist. He was a Soviet physicist. He was actually a Soviet spy. And he wrote in his memoirs, I guess, that he was actually a spy. And he said, no, I did it for the money. So I would say, was a Soviet spy, but he was the most capitalistic of them. So he was actually kind of maybe fighting from the inside, I don't know. So he actually writes, I did it for the money and my family position and so on. Anyway, so the debate was about the fact that quantum entanglement had a problem in the usual Copenhagen interpretation of quantum mechanics with relativity. And you may already know what that problem is. If you go back to the simultaneity argument that I showed you before, like in the hardcore Copenhagen interpretation of quantum mechanics, it should not be called interpretation because that in particular is proven wrong in that sense when I'm about to mention, but it's usually part of what is called canon Copenhagen interpretation, is that when you measure a system, you collapse the wave function, and that's the thing that is wrong, above all for a quantum information person. You collapse the wave function, and that collapse modifies the wave function and make it now look like an eigenstate of the thing that you measure. Back to the cat would be, the cat is dead nor alive. It's in a state that is not an eigenstate of the life operator. However, I measure, I find it alive, and suddenly it's an eigenstate of being alive. He is alive, because I found it alive. So that mechanism is called collapse of the wave function. It's rather incompatible with relativity exposed. Because again, think of quantum entanglement. And let's go and see, and this is what this is about, this quarrel is about. So this, the incompatibility of special relativity with the Copenhagen hardcore interpretation led Einstein to cast doubts on quantum mechanics as being a local realistic theory. And in particular, they give, well, he actually didn't get so far. They said it's either not complete or it's incompatible with relativity. There was a third option, which happened to be the right one, but in their paper, they actually work on assumptions. It's pretty logical. They don't make mistakes, but they think that either, so they don't want to give up. They actually admit either we give up local realism, or it's not a complete theory, or it's incompatible with relativity. Those are the three options. And they say, I don't want to give up local realism. Local realism, you know what it is? The physical quantities that we have represent objects in reality. They have physical reality. For example, when I talk about the position of a particle, I'm talking about something that exists physically. It has some existence. So that local realism, there is a value of position. So that local realism, Einstein didn't want to give up. Einstein had some prejudices during his career, but let me say, this paper is super nice in the sense that they don't say, I think that's holy, and I will hold it. No, it says, it's to me the most difficult to give up. Anyway, what got quantum theorem so much at odds with relativity? Well, quantum entanglement. Let's try to understand what quantum entanglement is by first understanding classical correlations, because quantum entanglement is just a fancy name for a particular kind of correlations. Actually, it's apparently a mistranslation from German, because the original, it was